and he is actually, in one way, the second generation Brånemark, because he took after the professorship after my father. So, Peter, the floor is yours.
Thank you very much, Richard Brånemark and Richard O'Donnell. Richard times 2, I was going to say as a joke, but you already know that. They spell their first names a little bit different. Thank you, organizers, and dear ladies and gentlemen, dear colleagues and friends. I'm an MD, but I've spent almost my entire professional life in the lab. That does not mean that I don't like interaction with patients. In fact, I think I was a pretty good MD. However, when you have to choose between curiosity in the field of cell biology and facing a program with patients every day, you find out that you have limited time for both. So I made a choice, and I'm a very happy person. However, what we do in the lab is important that it will have a bearing on the clinic. And the question is, what is the relationship between something called Nano Osseointegration and patients? I start with the definition of osseointegration. Osseointegration was a term developed for something that very few understood what it really meant. And with what it really meant, I mean the mechanisms behind osseointegration. The result became evident. Stability, transfer of load, function regained, totally or partially. But what are the biological mechanisms? And are there only biological mechanisms? Couldn't it be that material properties will also influence the biological response, which leads to implant stability and function? So this is the definition. I will also today tell you a little bit about what nano is. And with nano, we talk about a length scale 10 up to the minus 9 meters. So we are below what is typically recognized as a cell. And you have the cell size around 10 microns, as you very well know. Now we go down to the small molecule and atomic length scale when we talk about nano in perspective of biology. That does not mean that that length scale is the only determinant behind biological responses at implant surfaces, nor responsible solely for the function. So don't take me wrong here. Of course, it deals with what happens also on the organ level. Okay? So don't take me wrong here. I don't want to be accused of saying the only thing that matters here is on the nano level. But what I will try to tell you here is that this length scale can mean a lot for the interface between the material and the biology. So, some cell biology for you, maybe refreshing for some of you, maybe something else for some others. I will also talk about the structure of the interface. And why? Well, because the structure is closely related to stability and biomechanical performance. So, This is the scene. When you put in an implant, endoprosthesis or exoprosthesis, the surface of the implant meets a lot of different tissues, bone and soft tissue. So, what is the sequence of events in bone? Let's take bone by itself. Well, we have a sequence of events going from hematoma formation, clot formation, coagulation, fibrinolysis, complement activation, a cascade of messenger molecules which are released to defend ourselves from the surgical trauma, the surgery. However, with time, this initial cascade response, sometimes called inflammation, is followed by repair and regeneration. So, with time, after surgery and placement of an implant, irrespective of material, there is some kind of regeneration. Sometimes this is de novo bone formation at the site which has been injured. And that de novo bone regeneration is in close proximity to the surface of the implant. The bone is remodeled and it allows the transfer of load in different directions. Sometimes it is not, because sometimes you have a lot of very tricky indications. You might have tumor, you might have ongoing infection, you might have autoimmune processes going on. And here you are at a totally different situation. And that's why I think that knowledge in this field is very important for further indications of your treatment, which has now been proven to work in orthopedics. Osseointegration works in orthopedics. So, is all this true here, this sequence of events? Well, it has been believed that, for instance, I'm sure you have been taught that bone formation is a quite rapid response. You only need the recruitment of stem cells, progenitor cells, and differentiation of those cells into osteoblasts. Bone resorption, that is a late event. Remodeling is a quite late event. That is not true at implant surfaces. I'll show you. Here is a typical experiment that we do. This is an example. Rats, bone, implants, small ones, millimeter size, some surface modification. What do? We insert these implants in animals. We retrieve the implants. But then what most people do is that they analyze the morphology around the implant, and that's very important. Or with micro CT or X-ray. What we have started with is to analyze the cells that are present on the surface after unscrewing and retrieval with respect to what they are doing in the genome. So we analyze the gene expression of the cells present in vivo at the implant surface, because we want to come as close to the material surface as possible. However, it's also important to know the stability, and then we use different biomechanical equipment. Here are examples. One surface at the top left, very smooth, one more irregular just beneath. These are characterized in different ways using various surface-sensitive analytical tools. What happens? Cells, these big cells here, that's one of the most earliest inhabitants of this place. This is a stem cell. So we have stem cells at this site very, very early, within hours. However, we also have inflammatory cells present at this site, at this surface, at the same time. So what do they do, these cells? What are they doing there? Well, first of all, we'd like to know who are these cells. So you analyze a lot of genes which denote, for instance, if they are stem cells, what they express on their surface, etc. So we know we have stem cells here, we know we have inflammatory cells. Do they express something? Do they really do something? Do they do their job? And which job? So these are some panels. Alkaline phosphatase and osteocalcin, two genes that denote bone formation. Very rapidly, we have a triggering of those genes within hours at both types of surfaces, the smooth surfaces and the little bit more rough surface. However, there is a difference. One of these surfaces, the more rough, there you have a stronger expression of bone formation. Very interesting. How come? However, now comes the thing I alluded to before. Bone resorption, at least denoted as the expression of genes operative in the resorption of bone, they are expressed at the same time, very rapidly. So bone resorption is triggered directly as well. And we have a higher expression of bone resorption in vicinity of the rougher surface. Furthermore, we have inflammatory cells present. These cells typically express cytokines, tumor necrosis factor alpha, interleukins, etc. We have two examples here, TNF-alpha and interleukin-1 beta. That expression is higher on the smoother surface. What's the explanations? We have to start looking inside the cells. We look at transcription factors. Transcription factors are intracellular messenger molecules. Also inside the cells, there is a difference between these two surfaces in the cells present at these surfaces. For instance, with respect to a transcription factor called PPAR gamma. So, is this of any importance, you may ask? Well, I give you one example. The PPAR gamma is implicated as one of the most important transcription factors for stem cells moving into fat cells. However, the PPAR gamma might have a role for the differentiation also of osteogenic cells. Because the stem cells, they can go in different directions. So, what about this PPAR gamma, which is expressed in cells at the implant surface in bone? Let's inhibit that factor and see what happens. So that's what Cecilia Granelli has done in an in vitro system. She has blocked the PPAR gamma transcription factor in vitro in mesenchymal stem cells, human mesenchymal stem cells. What happens? Interestingly, the cells become more osteogenic. So suddenly we have a tool to drive mesenchymal stem cell into a preferential direction. Is this important? I don't know. But things like this could be of interest for you if you have systems, clinical systems, patients, where you might have very tricky conditions locally. I'm not going to dwell more on the genes. You might be fed up with them. I don't know. I don't take the risk. I jump. However, it's very important, and now comes the clue. The change, the expression of bone formation genes and bone resorption genes, and the differences between these two model surfaces, the smooth and the rough, is also expressed in terms of stability of that interface. It means that where we have a higher expression of bone formation and bone resorption, we have a higher degree of stability during the development of osseointegration. And this is important because it links what happens on the cellular level with what we can demonstrate using tools which are relevant for the clinical situation. Has this something to do with the nano level? Okay, I gave you one story more and then I will finish. This is a detail of that interface that I just showed you before. It's a high magnification. You see the oxide of the implant and you see mineralized bone. This is a backscatter SEM, scanning electron micrograph. Close contact. Let's now induce nanoscale changes on the surface and see what happens in vivo. So what we have done is to induce nanoscale surface features. What happens? Here is the surface modification in the valley of a screw, threaded implant. This is the high magnification. If you can see this fuzzy appearance. You see the balls here with a fuzzy appearance. That's on the length scale of nanometers. Does it matter compared to entirely smooth balls? Yes. This is what is the difference. To the right is a torque versus angle curve, a typical one for that nano modification. And to the left is the smooth. And what it tells us is that we have a very distinct break point and we have a very much higher level than with the smoother implants, without the nano features. Another table published, significant effects, early and late, which is important. We don't only want to have more rapid and stronger osseointegration initially, we want it to be maintained. Scanning electron micrograph, bone in close contact, exemplified by the deposition of calcium, the presence of calcium using elemental analysis. But why? Why do we have that greater strength? Then we need a tool to analyze the interface on the nano level. Do we have that tool? Can we resolve that interface? Yes, we have that now. What we can do is not only to do light microscopy, scanning electron microscopy, but we can do transmission electron microscopy. And what you will see here is, for the first time ever, sounds like a Paramount MGM commercial. It's not. This is the first micrograph that shows the border between living to the right and dead to the left. To the right, biology. To the left, material. To the right, hydroxyapatite. And you see the atoms, the atomic lattice, the ordered appearance of hydroxyapatite on the right. But on the left, you see an equally ordered titanium atomic lattice. So we have a meeting between living and dead where the atomic planes interact. This is in a human being, from a human sample, retrieved from, my dear friends, an amputation prosthesis. It's never been shown in dentistry, endoprosthesis, in general, I mean cemented, oral, etc. So you know this now. This is possible in amputees. I'm not going to dwell on the technique. You will hear more about that later today. But here comes the thing. This interface between living hydroxyapatite and titanium oxide is dependent on the interfacing between small nano-sized nanoapatite crystals and the surface oxide. And this interface we actually don't see with very many implants yet. So we know that nanoscale surface features induce such interface. This is complicated maybe for you, but it's even complicated for me working with this day and night. And why? Well, because science and clinical development deals with the methods we use, the techniques. 20 years ago, we had another set of techniques. And we wrote papers and communicated at conferences. These models of how the interface looks like have been presented, and now we come with a totally new interface using new techniques. So we had to scrutinize our previous statements, not only mine, but also my other colleagues, and finally see what is possible to achieve. But I can assure you, this high resolution we've never been in the proximity of before. Clinically, does this nano surface modification play any role clinically, you may ask? We don't know that, if it plays any role for amputees. But we know that in the oral field, these surface modifications have been introduced. And so far, it works very well. That's what I can say. There is one publication so far. Small study, short follow-up. It's okay. The term Nano Osseointegration, I use that because I think it's nice to have some new terms. We'll see what it will be. I don't bother so much. Let's discuss it in the future. What is of importance, before I take too much time from Todd, is that we are all heavily dependent on our collaborators and also on financial support. And this is our support from the VR Biomedcell Institute, Excellence Center. And I would like to acknowledge the group of scientists working here in Gothenburg with the amputee project that has let people like me into their world. Very interesting for us. And finally, here are some of the people that actually do the work. I only talk about it. No, it's not true, but they do most of the work. And it's an excellent group of people. We have also published, and here are some papers. And if you're interested, please get in contact with me and we can provide you with references and so on if you're interested in osseointegration on the cell and molecular level as well as nano osseointegration. And I congratulate Richard ×2 to initiating an osseointegration society focused on orthopedics. And I wish you very, very much luck in the future. Thank you.
Thanks a lot, Peter. And the plan now is to